counting. In this section, we're going to learn about the multiplicative counting principle, the additive counting principle, and solving problems involving the direct and indirect method. Previously, we discussed counting techniques such as enumeration, where we list each and every single outcome explicitly in order to count the total number of outcomes. We're going to be learning some organized counting principles to make us more efficient. And we've also used conventions like tables as well as tree diagrams to list outcomes, but we'll realize that that is limited in its scope because of its time-consuming nature. So, to start with the multiplicative counting principle, sometimes referred to as the fundamental counting principle or slot method, if a task or process can be made up of stages of different choices, then the total number of choices is m times n times p and so on, where m represents the number of choices in the first stage, n represents the number of choices in the second stage, and p represents the number of choices in the third stage. So we'll look at the following example to help illustrate. How many permutations of the letter A, B, C are there? And if you recall, a permutation is an arrangement in an order, where order matters. So, think of the number of choices you have for that first letter. This tree diagram can help illustrate that A, B, and C could have been in that first position. So we sometimes refer to our solution as the slot method here, where there are 3 choices in the first position, and then the next letter. In each case, notice that if A was selected first, it's not an option in the next stage. Because we can't repeat the same option, we're rearranging these letters. So if B was selected, A and C are the only other options. So there's 2 choices in the second stage. So we use these tree diagrams to illustrate a sequence of compound events, one after the other. And the number of choices at each stage can be used to determine the total number of outcomes. So here there's 2 choices, and then if you've already selected 2 letters, you must pick the remaining letter. There's 1 choice for that last stage. So notice that this tree diagram helps us see each of the individual outcomes explicitly. If we were to list these, this is enumeration. But we could have done this in an abstract sense using the multiplicative counting principle by simply multiplying the number of choices at each stage. 3 times 2 times 1 is 6, and that's how many of these outcomes there are. So this is a small case that we can use to verify that this multiplicative counting principle works. It also applies to a more abstract case, so we can extend our understanding. For example, a multiple choice quiz with options A, B, C, or D has 5 questions. How many ways can the quiz be answered? So we'll assume that each question is answered. You can take a second to answer this. And if we think of this as a sequence of choices, question 1, there are 4 choices for that first question. A, B, C, or D. And then 4 choices for the second question. And then 4 questions for the third question, and so on. So we can use the convention of exponents to write repeated multiplication. Instead of typing this into our calculator, it's repeated, so you might make an error. Try to abbreviate this using 4 to the power 5 and evaluate. And there's 1,024 ways in which this quiz can be answered. And you can imagine this would be challenging, if not impossible, to draw on a piece of paper. So we're going to try to extend this in a more general sense. Let's look at the following application. Permutations with repetition versus without repetition. And what I mean by repetition is that the option that is selected can be repeated if there is repetition. If there is not repetition, it is no longer an option in the following stage. So how many passwords are possible on a 4-digit iPhone lock screen with repetition? So as you can see, we have the numerals 0 through 9, which is 10 choices. Our first choice for our first digit in this position would be 10. We could have picked any of the numerals. And for our next step, 10 as well, and so on for each of those positions. We've learned that we can multiply those choices, number of choices together in each stage to get the total number of outcomes, and that ends up being 10,000 different possible iPhone passwords of 4-digit length. To change this question, how many passwords are possible on a 4-digit iPhone lock screen without repetition of numbers? So if we can't select that same number again, in our first position, we could have 10 of the numbers, any of the 10. But in our next position, there would be one less choice. So we see the following product: 10 choices, then 9 choices, 8 choices, because there's previous 2 options. We selected something, we can't use them again in this stage, and so on. This ends up being 5,040 outcomes. So take a moment to contrast the fundamental counting principle with the additive counting principle. If one mutually exclusive event can occur in m ways, a second in n ways, and a third in p ways, and so on, then there are m plus n plus p ways in which one of these actions can occur. So I'm going to pick a very simple example for you to think of. In the previous example, fundamental counting principle, we thought of compound events, one after the other in a sequence, and we multiplied the number of choices in each stage. This can be thought of as one stage. You are making one decision. A pet store has 2 cats and 3 dogs. How many ways can one pet be selected? Now note that each cat and each dog is considered different. They are not identical, so each is a unique choice. Do not overthink this. This is 2 plus 3, because we could have picked either of the 2 cats or any of the dogs. So 2 plus 3, and that keyword is or. I like to think of the keyword and then, or phrase. If I'm doing the multiplicative counting principle, I'm doing this task and then this task and then this task. That's multiplication. But in the additive counting principle, we learned that if we can do a task one way or another, we add those outcomes together. So let's look at how this can be applied in a more sophisticated manner. The partitioning set. A partitioning set lists all outcomes of a set into mutually exclusive subsets. And if I haven't mentioned earlier, mutually exclusive means that the 2 outcomes cannot occur at the same time. So an example of this would be an iPhone can have either a 4-digit password or a 6-digit password. How many different passwords are possible? So one thing to notice, a 4-digit password cannot also be a 6-digit password, and vice versa. It's one or the other, mutually exclusive. And this word that is highlighted, or, is a powerful word to signal that you need to use the additive counting principle. So if we want to get the total number of passwords that are possible, we should add the number of 4-digit passwords plus the number of 6-digit passwords. And we use a similar technique to our previous method. This is the partitioning set. All cases are broken up into 4-digit passwords and 6-digit passwords. This composes all possible cases into these 2 subsets. And we use fundamental counting principle to be able to solve for each and add those outcomes together. So this partitioning set can be helpful to solve problems. The direct method is a counting strategy that includes counting the outcomes that you are interested in, and the indirect method, a strategy that excludes outcomes from the total to deduce the total number of outcomes. So let's look at an example with that context. How many 4-digit iPhone lock screens do have repeated digits? So something to signal that you are going to use a partitioning set sometimes is if it says to do something or do not have some type of characteristic. So if it does or does not have some type of characteristic, if you can't directly calculate that, you might have to use the indirect method as you see here. We take all cases, which is repetition and no repetition, added together, and we are looking for the ones that do have repeated digits. So that's hard to calculate on its own, repetition. This is our target, or what we would like to isolate. Using opposite operations, subtracting no repetition from both sides and switching the left and right hand side, we end up with the next expression. All cases minus no repetition. So in general, we can take all cases and subtract the things that we don't need, the things that don't satisfy the constraints, such as do have repeated digits. The ones that do not fall into that category are the ones that do not have repetition. And that is easier to calculate. All cases without restriction is 10 times 10 times 10 times 10 for each of the 4 digits, and then subtract the cases with no repetition. This descending product with one less choice at each stage is what you come across whenever there's no repetition of choices, because there's one less choice at each stage. So we can evaluate this and determine the number of cases with repetition.